Division is probably one of the most confusing operations a computer can perform, so in this video we'll figure out how computers divide, as well as see a new way of representing numbers in a computer. To understand division, let's compare to division in decimal, but not just any division. We'll specifically look at long division. Let's do 500 divided by 4. The first step is to write this division in this form. We put our divisor, 4 in this case, on the left, and put our dividend, 500 in this case, inside this shape. The first thing we do is ignore these last zeros of 500 and just look at the 5 and ask ourselves, how many times does 4 fit in 5? The answer is once in this case, so we write a 1 above the 5, and then on the line below this shape, we write 1 times 4, or just 4. Now subtract this 4 from the 5 to get a 1 and write that below it. Before, we ignored all of the last zeros, but now, let's only ignore the rightmost zero, but keep the other one. So it's as if our new number here is a 10. Then once again ask yourself, how many times does 4 fit in 10? The answer is 2 of course, so write a 2 above here. Then below here, write 2 times 4, or simply 8. And once again subtract this 8 from its 10, which is 2. Now, we don't ignore any of the zeros anymore, and write a 0 here. We ask ourselves, how many times does 4 fit in 20? The answer is 5, so I can write this 5 above here. Then we do 4 times 5, which is 20, and subtract these two numbers. We get a 0, and we don't have any more digits left, which means that we're done with our algorithm. Our final answer is this number right here, 125. This long division algorithm can be pretty confusing, so let's look at a few more examples to get the hang of it. Let's do 20 divided by 12. Once again, we write it in this form. We ignore the last zero and ask ourselves, how many times does 12 fit in 1? The answer is of course 0. If the answer happens to be 0, you don't have to do any multiplication or write it above. We just add the next digit and continue the algorithm. So we ask how many times does 12 fit in 20? The answer is once, so now we write a 1 above it. We do 1 times 12 and write the answer below here. We subtract these numbers and get 8. Although it might not look like it, our algorithm has actually completed, because we don't have any more digits from our original dividend. What this 8 here means is that it's a remainder, meaning that 20 divided by 12 is 1 with a remainder of 8. Let's do one final big example in decimal, where we divide this number by 37. First ask, how many times does 37 fit in 1? 0, so we look at the next digit. Then, how many times does 37 fit in 12? Still 0, so we also look at the next digit. How many times does 37 fit in 126? This time it's 3, so write a 3 above here and write 3 times 37 down here. 126 minus 111 is 15, so write 15 on our new line and append the next digit. How many times does 37 fit inside 150? The answer is 4 times, so write a 4 above here and do 4 times 37 here. 150 minus 148 equals 2, so write it down here and append the next digit. How many times does 37 fit inside 22? 0 times, so we append the next digit. How many times does 37 fit inside 225? 6 times, so write that down and do 6 times 37. 225 minus 222 equals 3, so write it down and append the final 8. How many times does 37 fit inside 38? Once, so we do 38 minus 37 and get a final 1 here. Now we're out of digits, so our final answer is 34,061 with a remainder of 1. With this knowledge about long division in decimal, let's now try to do the same algorithm in binary. Let's do 13 divided by 5, or 1101 divided by 101 in binary. How many times does 101 fit inside 1? 0 times, so we look at the next bit. How many times does 101 fit inside 11? Still 0 times, so we look at the next bit. How many times does 101 fit inside 110? This time it's 1, so write it above here and subtract 101. 101 doesn't fit inside 11, meaning that our algorithm is complete. Our answer is 10, or 2 in decimal, and we have a remainder of 11, or 3 in decimal. As you can see, long division in binary is much the same, but the main difference you should notice is that the number above here can either be a 0 or a 1. This means that we don't have to do anything complicated with how many times it fits inside the number, but instead just ask yourself if it's greater than or equal to the divisor. So in our example, we didn't have to ask how many times does 101 fit inside 1, but instead we just had to ask is 1 greater than or equal to 101, which would have been a no, hence a 0. That's nice and all, but how do you know one number is greater than or equal to another number? Here's a neat trick. You can subtract them and then check if the number is negative. So we would do 1 minus 101 and then just check if the result is negative. If you remember from a moment ago, a 2's complement number is negative if the leftmost bit is a 1. So to check if one number is less than the other, we'll just put them in a subtractor and look at the leftmost bit. Let's do the same long division we did before, but now in actual circuits. As we said before, our first step is to check whether 1 is greater than or equal to 101 and look at the leftmost bit. Now we have to make a choice. If the leftmost bit's a 1, we do nothing and add the next bit. But if it's a 0, then we need to write a 1 up here and use the difference as our new number. If you ever find yourself having to make a choice in these kinds of situations, then what you're probably looking for is a multiplexer, or a mux for short. A multiplexer has this symbol. It has some inputs of a bunch of different numbers, a select signal, and one output. The way it works is that using the select signal, you can choose which of the inputs you want to have. So for example, in the 2 to 1 case, where you only have 2 inputs, you can have a select signal of 0, in which case the output is the first input, and you can have a select signal of 1, in which case the output is the second input. This behavior of being able to choose which of the inputs you want is exactly what we need for our divider circuit. Let's now go back to our divider circuit. As for our top output, Q3, this is simply not the leftmost bit we had. So 0 if we cannot subtract, and 1 if we can. Now for our mux, we want to use the difference between 1 and 101 if we can subtract, so if the leftmost bit is a 0, and we want to use a 1 if we cannot subtract, so if the leftmost bit is a 1. Let's then use the leftmost bit as our select signal and choose between either the 1 or the output of our subtractor. Let's now go to the next step in long division. We append the next bit we had to get a 1, 1. Then we do the exact same thing we did before. We just check whether we can subtract or not. If we can, we use the difference as our new number. If we cannot, we keep this old number. So just put another mux here. As for our Q2 output, we just use the exact same circuit we had, where we put a NOT gate in front of the leftmost bit. Then once again we continue this pattern. We append the next input bit and create the exact same circuit. Do it just once more and we have our full Q output of Q3 to Q0. The last output here at the bottom must have then been the remainder we have. This is the division circuit we've been looking for. If you want to divide larger numbers, you simply add more of these rows. But I know what you're thinking right now. What happens when you divide by 0? Well, let's go through it and see what happens. Let's do 5 divided by 0, or 101 divided by 0 in binary. In our first step, we check whether 1 is greater than or equal to 0, which it obviously is. So our Q2 output is a 1. Then we use our mux to get the difference between 1 and 0, that just stays 1. Then for the next row, we check whether 1, 0 is greater than or equal to 0, which it still is. So Q1 is 1, and we take the difference between 1, 0 and 0. That just stays 1, 0. Then we finally check whether 101 is greater than or equal to 0, which it still is. So Q0 becomes 1 as well. Our final remainder will be the difference between 101 and 0, but that just is 101. As you can see in the circuit, when we divide by 0, we just get a remainder of our original input and an output of all 1s. With these operations, you have the ability to do whatever you want with these binary numbers. You can even work with fractional numbers, because after all, our original pattern of adding powers of 2 doesn't just have to work for positive powers. Using something called fixed point notation, where we just put a binary point in our number, we can decide that to the right of this point, we want to use only negative powers of 2. For example, the number 0.11 would be 2 to the power of minus 1 plus 2 to the power of minus 2, or 0.75 in decimal. We can even do it with a 2's complement system, by just keeping the leftmost bit negative. For example, 101.01 would mean minus 4 plus 1 plus 0.25, in decimal, or simply minus 2.75. As for our arithmetic operations, this binary point luckily doesn't change anything. If we're adding 1.5 plus 2.5, that is the exact same operation as 15 plus 25, we just scaled it down by a factor of 10. Likewise in binary, 1.1 plus 1.0 is the exact same thing as 11 plus 10, just with the binary point back in the right place. The same goes for subtraction, multiplication and division. Each of those operations can be performed as before, simply by moving the binary point around. Other than the fixed point, there exists another really common way of representing numbers, called floating point numbers, or floats for short. Rather than our normal counting system, they work using a binary version of scientific notation. In decimal scientific notation, we have something called a significand, which is a number between 1 and 10, which you multiply by 10 raised to the power of an exponent, which can either be positive for big numbers or negative for small numbers. And just for some extra information, we could put a plus or minus sign out the front to show whether or not it's negative. As you can see, this allows these numbers to have a huge range of values they can represent, all the way from the very small to the very big. Which is exactly why floats are used in so many modern applications. Using floats, instead of a base of 10, we use a base of 2. In the IEE 745, people have decided on a set of standard encodings for floats. They made the half precision floating point, which uses 16 bits to store a number. Single precision floats, or simply floats, which uses 32 bits to store a number. Double precision, or doubles for short, which uses 64 bits. Quadruple precision, which uses 128 bits. And octuple precision, which uses 256 bits. Let's look at single precision for now. We have 32 bits to use. Let's use the first one to indicate whether a number is positive or negative. 0 if it's positive, and 1 if it's negative. Our next 8 bits are for something called a biased exponent. As you know, with 8 bits, you can represent any number from 0 to 225. But with our exponent, we also want negative numbers. We don't want to do this with 2's complement, because this will complicate our internal hardware. What people have decided to do instead is to bias the exponent, which means to simply subtract a number, which in single precision is 127. So if our biased exponent is 10010100, then normally you'd think it's 132, but because it's biased, we subtract 127, and our exponent is actually 5. A biased exponent of all zeros would be minus 127, and all ones would be 255 minus 127, or 128. Then our final 23 bits we have left are not for the significand, but instead for the fractional part after it. This is because, when you write something in scientific notation, the first digit is never 0. If it is, you just change the exponent until it's no longer 0. Knowing that it can never be 0 doesn't give us much information in decimal, because there are still 9 choices left for what the first digit might be. But in binary, there's only one number it can be, which is 1. Meaning that for a float, instead of writing the whole significand, we instead write only the fractional part after the first one. Let's do some examples to make it clear how you convert between floats and fixed point. 100.100 is the same thing as 1.001 times 2 raised to the power of 2. The number is positive, so our first time bit is 0. Our exponent is 2, so our biased exponent would be 129. 129 in binary is 10000001. So you can write those down for our next 8 bits. Finally, for a fractional part, you can just read off that that is 001 and then a whole bunch of zeros. So for our final float, we get this. Let's now try to convert this float to a fixed point number. The first bit is a 1, meaning that our number is going to be negative. The next 8 bits spell out 134 in decimal, but we subtract 127, so our exponent will be 7. Finally, we can use the fractional part to just write out a number. We have minus 1.11001 times 2 to the power of 7. Or in 2's complement, we get this number, which is minus 228 in decimal. You might have noticed that there's actually no way to represent 0 in the system. So the IEE have created a special format representing 0, as well as 3 other special characters. The number 0 can either have a negative sign or a positive sign, but both the exponent and the fractional part are all zeros. Infinity and minus infinity are represented using an exponent of all ones and a fraction part of all zeros. The sign bit indicates the sign of the infinity. Finally, you have the character not a number, or just nan. This is something you'd use when you have an invalid operation or value, such as when you divide 0 by 0 or take the square root of a negative number. Nan uses an exponent of all ones, and the fractional part should just be anything non-zero. The sign can either be positive or negative. So now that you know how to represent numbers using single precision, you can use the same system for half, double, quads, and so on. Here you have an overview of how bits are used in other formats, as well as the bias they use. With these videos, you've already learned a lot about how a computer would do maths, but have you ever wondered how to actually program a computer to do so? Click on this next video to learn more about assembly and how you can tell a computer what to do.